Alright guys, check it out. In number one, you're given the direction of an applied force, which is at an angle, and you're also given this ramp. You're given the dimensions of the ramp. It's 3 meters high, and we know the angle. If you're going to use your work equals FD equation, the force and the distance must be in the same exact direction. So if one is going to be at a 30-degree angle, then the other one needs to be at a 30-degree angle. So right now your force is at an angle, but your height is at a different angle. So what we can do is we can find the angle component of the distance using our 30-degree angle and using the height being 3 meters. You can use your sine function to find the length of the actual ramp. That length is in the same direction as the force, so then you can multiply force and direction together, or force and displacement rather. Okay, number two, change in kinetic energy is going to be kinetic energy final minus kinetic energy initial. Let's take a look at the actual equations. Kinetic energy is 1/2 mv squared, so you can simply do mv squared final minus mv squared initial. The only thing that's going to change is going to be the velocity, and you can find the answer. Remember that power is work divided by time, so the first thing we need to do is find the work. Well, you can do that. You're given the weight of the box, and you're given the height. So force times distance, which would be the weight times the height. Also mgh, it's all the same thing. So you can multiply your force and your distance to get the work, and then once you have the work, you can find the power. We have a transfer of energy here, some sort of interaction. So I'm going to set up my conservation of energy equation. Let's just stop for 1 second. Let me explain exactly how I knew to do that. Anytime you have a collision, or you're dropping something, or you're throwing something up, anytime you have an exchange of energy, you need to set up the law of conservation of energy, which is this equation right here. Potential energy initial, kinetic initial plus work equals potential final plus kinetic final. Okay? Anyway, let's look at this particular question and see what sort of input we have. Our input is we are exerting a force on a ball, so that's going to be work. And our output is the ball moves, so that's kinetic energy. So you're putting work in, you're getting kinetic energy out, so we can say work equals KE, or FD equals 1/2 mv squared. What are we solving for in this one? We're looking for the just the gain in kinetic energy. So that's all you need to do. Force times distance. Okay, number 5. Work equals FD. You got to remember your power equation here. Power equals work divided by time. Okay, number 7. Just remember that work equals FD, and also remember that they have to be in the same direction. If your force is to the sideways direction, then your displacement needs to be to the sideways direction. If your force is at an angle, then your displacement needs to be at an angle. In order for the equation to work, they have to be in the same exact direction. Okay, number 8, work equals force times displacement. Here's the equation for power, but you might remember this little trick we did in class. We can rewrite it with the expanded form of work, and then you see this fancy new equation, power equals force times velocity, which is going to be useful for question number 9. You're given some extraneous information there. You just need the power and the speed, which is 3. And what you're solving for is force. Remember for number 10 that work equals force times distance. Number 11, we'll skip this one. How about number 12? You're given a graph here. Remember that work equals force times displacement. So let's take a look at our axes here. On the y-axis you have force. On the x-axis you have distance. Work equals force times distance. So if you're multiplying the x and the y-axis together, what you're really doing is just finding the area. So you can go ahead and find the area under that curve, and that should give you the work. Okay, we have a force given at an angle, but the displacement is only in the x direction, so that's a problem. You have to put them in the same exact direction. The easiest way to do this would be to take your force vector and find just the x component of that. You can do that using your cosine function. And then once you've determined the force in the x direction, you can multiply that by the displacement, which is also in the x direction, and then you can find your work. Number 14, we're lifting a box. Work equals force times distance. And then to get the power, divide by time. And number 15, we have a transfer of energy problem. I know that because we're transferring energy from one place to another. We're starting at the top of the hill, and then at the end, you are at the bottom of the hill. So we're going to need to look at what type of energy we're starting with, that's potential, and what type of energy are you ending up with, that's kinetic. So we can say PE equals KE, or MGH equals 1/2 mv squared. You're looking for your kinetic energy at the bottom of the slope. So that should be the same as your potential at the top of the slope, right? Because energy is conserved. Keep this in mind, same thing for number 16. As you drop something, you're converting your potential energy into kinetic energy. Okay, number 17, you're pushing something. What is the increase in potential energy? Remember that potential energy is mgh. And you're pushing something on number 17, you're pushing it on a level surface. So it's not going up or down. Take a look at your equation. If you're not going up or down, what's going to happen to your potential energy? Let's remember the equation for kinetic energy, 1/2 mv squared. Let's plug it in. Number 19 is a conceptual question. What happens if you double the speed? Some of you guys can figure this out in your head. An easy way to do it is to just plug in fake numbers. So like make your mass 1 and make your velocity 2 or something like that. And then double the velocity and see what happens. Alright, we are falling from the sky in number 20. So we have a transfer of energy. So let's set up the law of conservation of energy here. When you're falling, what you're doing is you're taking PE and converting it into KE. So for any falling object, whether it's an apple or a human being, all you're really doing is you're taking that PE and converting it directly into KE. Number 21, in the from going from A to B, you're converting PE to KE. So MGH is turning into 1/2 mv squared. And then for the next question, you got to find the potential energy at point C. We can use our equation for potential energy, MGH. And the mass, to get the mass of the block, you can look up at number 21 there, or you can look at the illustration. 23, this is a basic potential energy equation. You're going to use mgh. Number 24, we're dropping something, so I'm going to set up my law of conservation of energy to think about what type of energy I have before when it's falling down, and then what type of energy I have after it strikes the ground. This one we have a little bit more information here, because not only is there potential energy, but we also have some sort of work here. How do I know there's work? Well, I know there's work because it says that you lose energy when you strike the ground. That is work. So we're starting with PE, we're losing some energy, and then we're ending up with KE. So let me set it up here for you. You do mgh minus 0.14, that's the work given in the problem, equals 1/2 mv squared. And you just have to find the KE. So that's the entire right side of the equation there. Number 25, a MOOC stands for Massive Online Open Course. And you should do it, for sure. It'll make you smarter. Okay, let's get into the word problem here. We have a piano at an angle. Uh-oh, I hate angles. It's okay. Let me tell you what to do. First, find the height. You're given the length and the angle. Use the sine function, find the height. Now, you got to find the work for lifting this piano up it. Well, work is just force times distance, mgh, whatever. It's all the same thing. So you take your force, which is given in the problem, multiply it by your distance, which is the height, because you're moving it up a ramp. So you multiply the force of the piano times the height to get the work. All right, so we're done with part number 1. For part number 2, think about what your transfer is here. You're putting in work because you're lifting the thing up off the ground. That takes work, right? Just like lifting weights. You're putting in work, and then at the end of the day, you're gaining potential energy. So work equals PE. Let's take a look at the third part. I'll walk you through it step by step. First thing, if you're going to release the piano and it's going to roll down the ramp, we have a transfer of energy there. So let's set up our law of conservation of energy to see what we're working with. Now, when the piano's at the top of the ramp, what kind of energy do you have? You have PE. When it rolls to the bottom, what do you have? KE. So we can set up PE at the top of the ramp equals KE at the bottom. So using this equation, you can plug in your numbers and you can actually find the velocity of the piano when it gets to the bottom of the ramp. So use that equation to find how fast the piano is going when it gets to the bottom. Now, once it hits the bottom, we have friction. So we got to find the acceleration of friction when it gets to the bottom. You can pull out your friction formula here, mu mg. The left side of the equation, force equals mass times acceleration. The reason I wrote it out like that is to show you that the masses cancel out. So to find the acceleration of friction, you really just have to multiply the coefficient of friction times g. So in this particular case, that would be what? 0.15 times 9.8 to find the acceleration. Okay, we're almost done. So we got our velocity, we got our acceleration. Now we need to find the distance, so let's just use our kinematics equation. How about this one? Vf squared equals Vi squared plus 2AD. Your final velocity is going to be 0 because it comes to rest. Your initial velocity is what you just found on the previous page. And your acceleration is the acceleration of friction that you just found on the previous page. And what we're solving for now is the displacement d. Alright, so the extra credit down there, I'm not going to write it out for you, but you're going to have to set up one of your collision problems. I think some of the classwork can help you with that one. So I wish you the best of luck with that. We got 3 more weeks, guys. This is the final stretch. This is the victory lap for our seniors. So I hope that you guys had a really good break. I hope that this video is helpful. I hope that you guys got together and figured out some of these problems. I look forward to seeing you in school.